How can we do this? Any suggestions?
So every periodic growth, we need to reevaluate the whole test data.
Yes, but here's the thing, right? If I just evaluate the pruning, right, in decision tree avoiding, so I'm getting ahead of things a little bit, right, but think of this as pruning the tree, right? I don't want to grow my whole tree, right? This is the analogy with actual, the actual agriculture, if you will, right? I don't want to grow the whole tree, I want to prune it, right? But based on what data, right? If you just do the pruning based on the same data that you were using to decide, which test was best in using information gain, then you're just going to make the same decision, right? So you have to do something different from what you were doing before, okay? And there's more than one thing that you could do, but, any suggestions? Any suggestions you might remember from your you have a suggestion?
Split the training data into two different separate data sets.
Absolutely. This is a very simple thing to do, and it's golden, right? Let your algorithm do what you yourself should be doing, which is don't have the algorithm look at all the data at training time. When you give the data to the algorithm, the first thing that it does is randomly, very importantly, randomly take some of the data for training and save some of it for later. And then what the algorithm does is, it learns on the training data, right? And then it has a very big tree that's probably very overfit. And then what it does is it sets that data aside and goes and looks at the new data. And now based on the new data, it starts cutting back. And as long as that data says that you're cutting back okay, you keep cutting back, and then when it says no more, you stop. Okay? Simple strategy. There's a couple of disadvantages to this strategy. What might they be?
Well, you have less training data.
That is the killer one, right? If you had 100 examples and you took 50 of them for testing, right, now you only have 50 to learn on, ouch, right? You could actually do worse this way. Sure, you'll be doing better pruning, but you learned the first 350 examples instead of 100, so the tree is so bad that, remember, pruning is just finding the best subtree of your tree, right? So if the tree sucks, the result will suck too. This is one disadvantage, but there's also, this disadvantage is going to be particularly bad when you have a lot of data or little data. Little data, right? In these days of big data, this actually sounds like the method of choice, right? I have data up the wazoo, right? I can split it, 10 times and still have enough data to learn. So in this case, not having enough data to learn is not a concern. As a little parenthesis, just because I have big data doesn't mean life is easy, because for the particular decision that I'm making right now, maybe I don't have a lot of data. But let's suppose that I really do have a lot of data, which in many cases I do, right? Then, splitting some of it off for validation, as it's called, you create a validation set or a pruning set, is okay. But then what's the problem? In the big data regime, there's also the problem.
The trees get pretty large if you have a lot of noise.
Exactly the problem, and this is the killer problem, is efficiency, right? Look back at this example, right? The decision tree that I want to learn only has 10 nodes. Beautifully simple. And beautifully quick to learn too, right? Remember, the bigger the tree, right, the more, cycles it's going to take to learn it and apply it too, and more memory to store, right? But, I actually went up all the way up to 100 examples thinking I was improving. And guess what? If I have a data set of, 300 million examples, or let's say a billion, right? All the users on Facebook are, it's pretty close to a billion these days, right? Well, that's a lot of data, right? I can learn a lot of stuff. But let's say that, even just 10% of that is noise, right? That's 100 million noise data points. So I'm basically going to grow a decision tree of size order of 100 million. Well, let's suppose that my decision tree that I wanted to predict whether to put this banner ad in front of you or not just have 10 nodes. Right? Notice what I did here. I had a decision tree that was 10 nodes, but I accelerated past it to a decision tree with, let's say, 200 million nodes. And then, I have to cut back. Even saying my pruning works really great. Right now I have a good decision tree, but the resources that I had to use for this were just orders of magnitude greater. And remember, the cost of learning a decision tree is at least for many of the algorithms, it's super linear in the size of the data. Even if it's just quadratic, right, going to 100 million versus going to, let's say, even 100, right, is just prohibitive. So pruning like this often works better, but it has these two problems. If you're in the small data regime, it actually could hurt you more than it helps. If you're in the large data regime, it might be a wonderful thing, but you just don't have the cycles to do it. Or you're not willing to wait that long. Okay? So, what other methods can we use?
You could prune as you went. So each time you added a node, you could say, does my held out data say this is a bad idea?
Precisely. So, pruning so the obvious solution to not growing the tree and then shrinking it is, well, don't grow in the first place, right? I need to decide as I go that I want to stop growing here, right? But notice, now I really cannot do this on the validation set, because if I do this on the validation set, it's not the validation set anymore. Right? What makes the validation set powerful is that I'm only choosing among a small number of choices there. It's the different subtrees of the tree that I could have. At learning time, I'm actually choosing among an exponential number of choices, so I really consume the data quickly. Right? So we have that problem. We have to do something different there. Right? So what might we do? Right? What's something that we might do, if you can recall something from your Stats 101, right? This is actually something from Stats 101 that we can actually plug in here. Any ideas? Yeah.
It's up there.
Yeah, of course, it's always up there. Okay, so tell me what's up there.
Well, I guess you could have some kind of test of whether there is significant improvement in the next layer or next layer of the tree or not.
Exactly. Statisticians are very fond of this, right? Significance tests. You may not remember this or have ever learned it, right? But there's these things called contingency tables, and I compare two distributions, and I try to decide whether they are the same or not, right? If they're exactly the same, then, things are good, but there's always noise, right? So the thing is if this is a distribution, and is this other one a noisy version of this distribution, or is it really a different distribution? Right? And this is exactly the situation that we're in here, right? We can use accuracy or information gain to pick the best attribute. But then we can apply one of these statistical tests like, chi-square, for example, right? A very widely used test of this type. But there's others, but let's say chi-square. This is the one that you're going to have in your project, right? I use a chi-square to decide, is the class distribution that I'm getting now significantly different from the class distribution that I had before? If it is significantly different, then I'm not overfitting, right? Because I'm modeling the class distribution better when I have this attribute than when I don't. On the other hand, if they look close enough, right, and the less data you have, the harder it is to tell, of course, then maybe I should stop because I'm not confident that I really have a different distribution, and at that point I really might be overfitting. Okay? Everybody follow this? So this is option number 2. In fact, historically, this was the option that people started out using first. So Quinlan, his first system was called ID3, and he used, pre-pruning with a chi-square test. You actually have a pointer to his original very famous paper where he does this. It's actually, fairly simple and straightforward. Okay? And, it really makes a difference. But then, he started finding that, this kind of pre-pruning, as it's called, right? It's kind of, if you think about it from the gardening point of view, pre-pruning is a very weird notion, right? How can you prune a plant before you grow it, right? But in decision tree terms, you can talk about it as pre-pruning. He actually found that pre-pruning was very bad a lot of the time. And in fact, if you do post-pruning, which then became the norm, you could do much better. And in fact, we've already seen it, and then he had this system called C4.5, where both of these are available on the web, by the way, where he did post-pruning. And then, the data mining explosion happened, and he created a startup and got rich and retired. And that's a good outcome, I believe. And then he just, actually the other day, he just won the award for, the CKDD Innovation Award for the very best data miners in the world, and he, very deservedly won it. Okay? But anyway, what is an example of a problem where this kind of pre-pruning fails miserably? We've already seen it, and not long ago. You want more hints? I can give you a visual hint. This is not a trivial question, right? So don't be ashamed by requiring hints.
If you use all the tests, you assume some distribution of the data,
Mm-hmm.
right? And it could be an E.
No, right, but in particular, so I agree, but let's try to think of a very simple, let's say, Boolean example, right? Where pre-pruning fails and post-pruning succeeds.
It's when previous levels of the node don't really show much improvement, but later on at the second or third level will improve the tree.
Yep, 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 yep. Remember this example? Why does pre-pruning fail and post-pruning succeed here? Well, first of all, does pre-pruning fail here? Parity, right? What is the problem of parity for pre-pruning? Is the distribution of the class significantly different when you have split on x1 and when you haven't? Heck no, it's exactly the same. Right? There's nothing to be had here. Clearly not significant. Right? So clearly pre-pruning fails here. What about post-pruning? Post-pruning is more interesting. What happens with post-pruning here? So post-pruning, to recap, is like I just barrel on. I keep growing the tree with any attribute that I have. If there's a tie, I pick something. If they all have 0, I just pick one and hope to get lucky in the future. Right? So what would post-pruning do here? Right, I'm at the root. I need to pick one attribute to split on. Right? What's going to happen?
You just have a root node?
Yeah, what I'm going to have is that one of three things is going to happen. I'm going to have x1 as the thing that I split on. Is this good or bad? This is good, right? That's what I want. Or x2, which is still good, right? On the other hand, I could also have x3, right? They all look the same, right? So, but in this case, I actually have 2/3 chances of picking the right thing, right? And if I pick, on the other hand, I do run the risk of picking the wrong thing. And imagine if there were 100 irrelevant ones, then I almost surely would pick one of the wrong ones, right? Which is why even post-pruning does not entirely solve this problem. But yet it does something useful, and depending on the problem, it actually may be enough. Why? So first of all, let's suppose that I had split on x1. Okay? Now what happens? Who do I split on next? Let's say I'm in the branch x1 is true, right? And I'm among the examples where x1 is true, so that's these ones here, right? I am trying to choose between splitting on x2 and splitting on x3. What do you think I should do? X2, right? x2 is perfect and x3 is noise. So I had to get lucky the first time, but the second time there is no luck involved. Okay? Same thing if I had picked x2 first and then x1, right? Okay, but of course the tough case for us is, what if I had split on x3? Now what happens? Who do I split on next? This is not the hardest question you'll have in this class. After I split, unless you're like, what do they call it, Buridan's ass, right? Who was between two bays of Halen stars because he didn't know which one to pick. So we split on x3, right? So what are we going to do next? Exactly. It's going to be one of two things, right? I either pick x1 or I pick x2, right? Are those things good or bad? They're both good, right? And then after I split on one of those, what happens next? I split on the other, right? And then we're done, right? So moral of the story, in all cases here, I wound up learning the right concept. Right? So things were not so bad. But however, right, if you look at the decision trees produced in each of these cases, which one would you prefer? The one that started with the split on x1 or the one that started with the split on x3? The one where you split on x1, right? Because the other one has garbage in it. Right? The other one, isn't going to give you any insight. In fact, it's going to mislead you into thinking it's something important that isn't. And it's, of course, this is a toy example, but, it's going to cost you more to store, more to use, more to apply, etc., right? So it still have been better to, find one of the others, but hey, with post-pruning, we actually found this one, okay? However, this is a somewhat optimistic situation, right? Because what's going to happen in the real world? Let's suppose that you have, 2 relevant attributes or even 10, but then you have 100 irrelevant ones. What's going to happen there? I split, probably the first thing I do is split on a bad attribute, right? And then, what do I split on next? Another bad attribute, right? And I keep splitting on bad attributes. And what is the problem with splitting on bad attributes? Is that after each split, I have less and less data. Right? I get exponentially less data. This is called the splintering problem, that as I grow my decision tree, I'm exponentially peeling away parts of the space and I'm zeroing in on small parts that eventually have no data in them. Right? So I'm actually wind up with pure noise. I never got around to my good attributes. Now what will happen on a good day is that I will get some mix of the good and bad attributes in there, and this actually often happens in practice, is that I learn a very big decision tree, most of which is garbage. But it's got some good stuff in there, so for prediction purposes it still does better than chance and might be good enough for what I need. Okay? It depends on the ratio of good to bad attributes and how difficult it is to figure out how the function depends on the good attributes. Okay? So the moral of the story is, post-pruning is much better than pre-pruning in this respect, right? Pre-pruning always fails. Post-pruning has a chance, right? But nevertheless, it's still not perfect. But there is nothing perfect. Okay. Okay. So any questions so far? Okay. There is one more method that is also quite popular that we want to touch on. So we've seen two methods so far. We've seen we stop growing the data when the split is not statistically significant, and we've seen growing the full tree and then post-pruning. Right? There is a third method, which you also use when you don't have a lot of data. When you don't have a lot of data, and say you don't like this whole notion of statistical tests and whatnot, what else might you do? Any ideas? This is probably not obvious, but it's a good example of the type of strategy that people use in machine learning all the time. And the strategy goes like this. Actually, I don't know if I have that here, but yeah. So we've already looked at these two cases, and now we're going to look at this third case. What we're going to do is we have an evaluation function, right? Let's say the information gain or the accuracy, that doesn't quite do what we want, right? So let's change it. Let's change it to an evaluation measure that is more likely to give us what we want. This evaluation measure now, of course, is not going to do as well on training errors, just optimizing the training error, right? It couldn't. But hopefully it moves us away from training error, but towards what we would really like to have. And people are very creative in coming up with measures of this type, right? Use your creativity, add something, to that, error or information gain that will help you induce a good tree. Can you think of what such a thing might be? Again, there's many options, but let's try to think of a simple one.
The size of the tree?
Exactly, the size of the tree, right? Usually the trees that are overfit are very big. So even without looking at any validation data, that as your tree is getting larger, you should start to worry. You don't know exactly how much, exactly when, but you have this general feeling that the bigger the tree is, the thinner the ice that you're on. And so you should just have a heuristic based on that. Take your error measure and add to that a penalty on the complexity of the tree. Let's say, the number of nodes. Again, you could do very fancy things there, but a lot of the time you don't need to. Let's just say the number of nodes. Okay? And so now what has to happen is that when I grow the tree, it has to be improving my accuracy by more than the complexity penalty is costing me. Okay? So I will allow extra nodes in my tree, but they have to pay for themselves by more than a certain increase in accuracy. And how, now you think, well, okay, but how do I weigh these two things? Well, maybe for that you can use holdout data. Or you can use holdout data to pick, the coefficient on your complexity penalty that trades it off against accuracy. Okay? If you don't have a lot of data, this could be a good thing to do. Some people prefer, significance tests. Some people prefer complexity penalties, but those are both viable options. If you have a lot of data and you have a lot of cycles, just do post-pruning. It's unlikely to be beaten. If you have a lot of data but you don't have a lot of cycles, you might find yourself back doing one of these two things because you can't really afford to do, the full growth and then the full print. Okay? Questions? So this measure, by the way, this method of growing the full tree and then post-pruning is usually is often called reduced error pruning. So reduced error pruning is where you're pruning by the reduction in error that you're getting as you prune, okay? And you have a validation set, okay? So you split your data into training and a validation set, and then you learn your tree on the training set, and then what you do is You look at pruning each possible node, see how much that improves your error in the validation set, pick the best one, and as long as you keep getting an improvement, you keep pruning. When every possible pruning left that you could do only hurts the accuracy on the test set, that's when you stop. Okay? And in fact, unlike the growing stage where things are basically heuristic at the end of the day, if you do this, you can actually prove that you get the best decision tree on the in terms of validation error. Okay. Questions? Okay, now there's actually another. So before we go on to that, here's what happens on the diabetes data set when you do reduced layer pruning. And again, this is fairly typical. So I grew my whole decision tree, remember, all the way to here, and now I'm here. Very bad tree. And now I start pruning. And guess what? I start getting better and better and better and better and better until I finish here. Brilliant. Actually, in this case, the post-pruning pretty much aced it. Okay, we could have gotten a slightly smaller tree, but we got just about the best accuracy that we could. Okay? So it worked in this case. Quick question. Notice that the curve that I get on the way back is above the curve that I get on the way there, right? Is that an accident or is there a reason for that? If I'm asking, it's probably because there's a reason, right? So that was more of a rhetorical question, right? What might the reason be?
Because you only prune if you get better.
Yeah, because notice, right, when I'm pruning, right, now I'm actually here's the key thing, is that the nodes don't get pruned in exactly the reverse order to what they got added, right? If the first node that I pruned was always the last one that got added, the two curves would be exactly the same, right? But they don't. When I start pruning, I actually have the choice of pruning any node anywhere that I want, and I pick the best one. So in general, that one's actually going to be better than, it's going to be better to prune that one than the one that, I happen to add last, right? I added one over here, but there's actually an over that I'm better off pruning. Okay? So, reduced layer pruning can be very good, provided you have the cycles in the data. Okay. Questions? Very good. So